a regular customer or a regular participant, a regular group coming and working with the group at Telluride, and there you go. This is really the group at Telluride. Also, Mike has brought a lot of equipment at Telluride with set up equipment and do all kinds of very exciting things with robots. And I guess now Mike is going to tell us about the new things coming out of Intel in terms of Loihi. Mike, I'm sorry that Intel didn't do very well financially. I hope your group survives, you know.
Oh yeah, that's overreaction. You know the markets.
Yeah.
All right. Yeah. Well, thanks, Andreas. Let me share some slides here. I will give you a little update on our program. I mean, we don't have a lot of time, and I'm assuming. I mean, certainly, if this was a normal Telluride, I would assume that most people have, would know very well all about Loihi, our neuromorphic chip. And I've probably heard my introductory talk, once, if not many times. So I don't plan to do very much in the way of kind of basic intro overview on our chip and our program. I'll tell you, a little bit. But I'd like to get into, kind of like some of our latest results that we've had maybe since the last Telluride or, in the last year recently. And yeah, share our latest quantitative summary of what we're kind of the picture that's emerging from all the various experiments and development that's going on with our systems. And maybe if we have time, some ideas or an idea about, like looking ahead to the days when we can all get together and, get in the lab and actually, build stuff again. What demo ideas could we think about? That's always a fun Telluride kind of topic. So we'll see. Hopefully we have time for that. So just, everybody, I'm sure you've heard it, over and over again, but just to remind everyone what we're doing with neuromorphic computing, what we see it, how we see it fitting into the general landscape of computing. So, we have kind of the way that we look at things. Obviously, you can slice computing up many different ways, but we have this spectrum here. If we focus on the interface between computing and memory is maybe one of the most obvious dimensions here that we can focus on. And in many ways, there's all these different approaches heading to the right, just like we've just heard about with Cerebras. It's another kind of approach in moving to the right on this spectrum. We're taking the inspiration from the brain, we're breaking down this von Neumann bottleneck that has served us actually so well for so long, for 70 years. This von Neumann model, standard computing on the left, is really, really good in so many ways. Obviously, it's changed the world, and it creates a really nice programming abstraction, which is one very important aspect of that. But we're moving to more of the form of what we find in the brain in terms of tight integration between the memory storage elements and the computing elements, which involves moving away even from what we regard as parallel computing today, which is really data parallel computing, which is really wide vectorized dense data paths that as long as you sufficiently activate all that real estate, all the data path resources, you're getting really efficient results. You're getting sub picojoule, 100 femtojoule MAC operations or less. But of course, if you veer into this sparse regime that you were hearing all about just now, which is exactly the regime that the brain operates in, all of those legacy computing technologies are terrible, and they fall over, and you're getting far worse efficiency. And what's more, there's all these other exotic properties that we see in the brain, and in fact, there's nothing stopping us from just harnessing some of those, understanding them, and mapping them into chips today. And take a bottom-up approach from the neuroscience, trying to understand and replicate the structures we see, and take a top-down approach from the theory and the algorithms, and try to guide what we arrive at in the middle in terms of building actual chips and technology. So that's the regime we're exploring in our program at Intel, our neuromorphic research. You know, these are some of the properties we're looking at. You know, none of these I'm sure are new, but event-based computing, expecting to get low latency, adaptation, so having plasticity rules embedded, you know, in this mesh network itself, and expecting to get really great efficiency and low latency computing out of that. So with that, this is, you know, the chip that we built on the left is Loihi. You know, this is just the basic kind of chip plot. You can see it's, you know, all of these emerging neural chips look really homogeneous. So it's these many core array structures, and that's what Loihi is. It generates spikes. So event-based messages basically are what these are. Under certain temporal conditions, when neurons get sufficiently activated, they generate these messages and they get sent around the mesh. And that's the spikes, and the whole game is how to program these things to make that, you know, do something useful. So what we built, I mean, one of those photos that Andreas shared there was our Capoa Bay 2 years ago at Telluride, where it was just built and we thought it would be up and running. We were handing them out to people, you know, trying to get them working at Telluride 2 years ago. And in fact, it took us several more months after that to finally debug the thing and get it fully working. But we got there. And so now we have these Capoa Bay USB form factor devices that we share with our research partners. We've got, you know, numerous, I don't know how many, couple dozen all out at different labs around the world. Then we have our larger systems on the right there, this Nahuku, and most recently this Loihi Spring system, which is scaling up and kind of pursuing this kind of really interesting scalability that we see in you know, biological brains, and seeing what we get by adding more and more scale. Certainly for deep learning, it worked really, really well to go to high dimensionality, you know, many, many parameters, figure out a way to train these things, and you get, you know, fantastic functionality. We would expect that with a different class of algorithms that are more suited to spiking neural networks, we should be able to similarly get great gains at this high end of the scaling spectrum. So we're exploring that too. And this Loihi Spring system, in fact, is, let me go to that slide. That is our latest system, and just I think it was in March or so we commissioned that. We got it booted up and running, and it's you might call it the densest neuromorphic system yet built. So I mean, there are bigger ones, you know, Spinnaker, the whole. I think they have a billion neuron system, which fills, you know, basically a data center. This is a 5-rack unit, well, a rack-mounted system, a chassis, which has, you know, kind of a fraction of a cubic meter of volume, and in that we've got 100 million spiking neurons. I think I calculated this happens to be 100 million times more dense than the original perceptron. You know, back in 1960, had 16 neurons in a big cabinet, and so now we're at 100 million spiking neurons in this, you know, amount of space as a 5-server system would take in a data center. It's 300 watts, you know, so that entire system is, you know, pretty remarkably low power. And in fact, normal operating condition would be even less than that, 100 watts or so, running a workload. We have been working on algorithms and applications to map to this. And so the first one we did here, which we published this in the NICE proceedings just last month or so, is writing up this work we did with implementing nearest neighbor search on Loihi Springs. So this is, you know, a classic machine learning 101 kind of problem. It's basically find associative search problem, basically. You know, given some input pattern, you've got a stored database, find the closest match to that input pattern, or find the K closest matches. So, you know, here's an illustration of how this is working in the algorithm we've mapped into Loihi and scaled up. So, you know, with images, you're just giving, supposing you have this image of a you know, a database, these are CFAR images here, and you corrupt one of these, well, you're expecting it, of course, to find the uncorrupted version. So you're doing an associative search through this database. And what we're doing is that we're applying kind of a PCA-ICA transformation to this and storing all the patterns in a sparse form where we're encoding the information across this transformed lower dimension representation of the image with spikes and temporally coding the spikes, so that once we do that transformation, you can see this is the input pattern that's getting sent in. It's a spike, temporally coded thing. There's no repetition here. This is not a rate code. It's a one spike per dimension here that we're encoding. And of course, many of these are very low valued, so they're coming late. But overall, it's quite sparse, and the earlier spikes indicate more prominent features in this input image. And so on the output side, the response is exactly the same encoding. We get this temporal output stream of spikes, and the earliest spike that's produced is corresponding to the closest match. And if you want more matches, well, you do nothing. You just sit there and you wait, and you get more spikes that come out, which indicate the other, 2, 3, 4, the other patterns that are close to it. Now, this is, very different from how you might implement k-nearest neighbor on a CPU or a GPU. A GPU is great at, say, batching a brute force implementation of this, which would be a big dot product matrix computation of, perform the dot product of the input across all the database elements. The hard part of that is doing this sort of finding the closest matches. By using this temporal coding of information and computing the dot product in time, we don't have to worry about sorting itself, because time sorts the answers. So we've mapped that into Loihi Springs, and it's basically a brute force implementation of k-nearest neighbors. And so we can just scale this out. We just map the whole database across the entire system, and we feed the key in, and it just kind of percolates through in this kind of wavefront, the key through the 768 chips in the system. And then likewise on the output end, the match spikes are kind of also percolating. I don't have an animation, unfortunately, here on this slide. But the spikes are basically diagonally kind of percolating out of the system. So there's just this single wavefront of computation basically that's moving through the system. And this gives very low latency. I think we're basically, going back to this, the stats here, we're as fast as any of the most optimized k-nearest neighbor implementations on a CPU. And this is being such a mature area. There's, gobs and gobs of, man hours and, attention that's gone into optimizing these conventional implementations. And just with the simple brute force, just spatial temporal matrix multiplication, we're getting as fast or faster than these conventional implementations. We can also generate and map the database to the system extremely quickly. So modern nearest neighbor search algorithms that are accelerated so that they can run within milliseconds, performing these matches, they require a lot of upfront optimization of the database, transforming it, building data structures that are organized in tree structures so that you can efficiently go through and match quickly. We don't have to do any of that. We just take the raw data, we pass it through this single matrix to transform PCA, ICA, and then we just layer this out into the system. So that gives us very low pre-processing time, and it also allows us to add new patterns to search to the database in order one time. There's no recomputing of all these carefully crafted data structures. We just immediately just program it into the database, and it's available. So ultimately, that gives 600 times better energy delay product than if you were to implement the same algorithm on a CPU. So energy delay product being a measure of computing efficiency, we're getting a nice 2 orders of magnitude, almost 3 orders of magnitude gain compared to conventional architecture. So that's nearest neighbor search. Another recent algorithm we've been working on and benchmarking. So this has actually been around a long time. There's a bunch of, as you may know, there's a bunch of different ways to try to implement stochastic optimization, constrained optimization problems in neuromorphic chips and spiking neural nets. And so we have one implementation running on Loihi, and it's what's novel about our implementation is that it actually uses some of the more exotic features in Loihi, like our multi-compartment capability, being able to basically build more complex neuron models that are going beyond just a simple leaky integrating fire that most people would assume is what your spiking neuron does. We can build more complex neurons that can compute more flexible things in this kind of computational graph that we've spread out, to represent the Sudoku problem. And what we're using it for in this case is to do an online calculation of the number of constraints that are violated, the energy function basically of this Boltzmann machine model of the constraint optimization objective. And so that what that allows us to do is actually detect when this network has found a solution. So it's stochastically, through noise injected in this network, this spiking neural network is exploring the state space. And that's what this plot here that's shown in this animation that hopefully you can see is showing the number of constraints that are violated. And so as that goes to 0, we want the network to detect that it's happened to stumble on a satisfied solution and stop. None of the other neuromorphic solutions have been able to do that. They've required an off-chip CPU to be continually monitoring the state of all the neurons in the system and then computing this offline and then stopping the chip or the system. And of course that doesn't scale, that slows the whole operation way, way down. So by having this embedded in the neural network itself, we can be running at less than 10 microseconds a time step here as we're searching through, and that means we can find solutions in millisecond timescales for relatively non-trivial constraint satisfaction problems. And so this is here some quantitative results from that, and we've compared it now to a CPU-based solver, the coin or branch and cut algorithm, which is a comparable type of solver that is not doing any kind of an exhaustive search or anything. It's not I've forgotten the term for this, but it's basically, it's not guaranteed to find a solution, but it will, opportunistically look as well as it can to find a solution. So it's a comparable CPU-based solver. It's certainly used for this kind of an application. And here we see, here's the scaling behavior of Loihi in blue to the CPU in black. As we scale up the problem size, you can see that we're consistently down at 1 to 2 orders of magnitude faster and lower energy than a CPU solving these same problems. So this is measuring the time from starting to when it arrives on the first correct solution. So this is, at this high end, these are pretty non-trivial problem. I mean, these are taking a CPU several seconds to solve this, and we're solving this on the order of 10 milliseconds. So this is pretty interesting because constraint satisfaction solvers and constraint optimization in general pops up everywhere in any kind of planning tasks, in motion and dynamical behavior. You're solving, our brains are solving optimization problems effortlessly. And so that network I just showed is not necessarily literally what we would think is going on in the brain, but it's certainly capturing something about the stochastic kind of exploration processes that are happening in our spiking brains with noise involved. So it's very interesting, and this is the first case actually of this algorithm actually measured rigorously, showing that in fact, yeah, this will actually run extremely well on neuromorphic hardware. Let's see, another example is smelling. So Loihi, this is some older work, but it was just published this year, which is really kind of captures, I think, the spirit of what neuromorphic computing should really be about, or at least it should cover this end of it very seriously, which is taking the actual neuroscience models. So in this case, we're working with Tom Cleland at Cornell, and he studies the olfactory bulb of mammals. So this is the system that smells and classifies odors, pattern matches to what's coming in from the sensory neurons. And he has these biophysical, very low-level models of looking at kind of the oscillatory processes that emerge from that behavior. And with him, Nabil on our team and Tom were able to abstract these models up to a level that could then be mapped into Loihi and run. And this is not an obvious network. It's not an obvious algorithm. Coming from the standpoint of conventional computing, you would not think to implement something like this. It just wouldn't be intuitive. But when you're taking this neuroscience-based approach and you're thinking in terms of spiking neurons and the kind of, seeing what's going on in the actual circuits based on simulations and even biological observations, it is intuitive. And so what's happening is that there's this rhythmic gamma cycle. The brain is filled with rhythms. And if you heard Fritz Summers' talk yesterday, you can see some of the theory, the great theory that's, we're extracting from that and trying to move it into the, more of a formal understanding. But here is a case where the oscillations are very mechanistic, and this network was devised without theory. It was just devised basically observing what these oscillations are doing. And in this case, what's happening is that the input odors are stimulating, this kind of relatively high dimensional vector of very messy overlapping representations of these receptor fields of different chemical signatures. And that leads to this, similar to the KNN example I showed, it's got this spatiotemporal pattern, this phase code that enters into this circuit. This is a recurring oscillatory circuit. And so as it cycles through, if you saw that animation, what's happening is that the stored patterns is projecting fragments of these little spatiotemporal patterns into a higher dimensional representation of fragments of timing alignments. And so through time, this network is oscillating and searching, doing this kind of parallel search process where it finds and pulls as an attractor dynamic. It's pulling this phase alignment of this input sensors to a stored pattern. And so that is basically another matching process, similar to that KNN example I showed. And we can use that for classification then. So we've measured, how well then this algorithm can, given training of a chemical odor database, how well it can correctly classify corrupted version of those from the database. And it, the other, I should mention, the other really novel thing about this network is it has integrated learning. So with some of the plasticity rules that Loihi supports, we can, in one shot, over the course of those gamma cycles, if you present it with the clean odor, a sniff, basically, of a clean version of these, or a representative sample of this odor class, it will just learn the timing, those phase alignments, and kind of project that and store it, capture it in this very fast learning process. And so with that single example that we presented to this network on this data set, we can then go and see how well it generalizes and correctly classifies the other orders. And with that single example, the EPL, this is the Loihi algorithm, gets up to a 92% level of classification accuracy. And all these other more traditional machine learning based methods are performing far worse with just one data sample. So a deep autoencoder, the deep learning approach, of course, deep learning we know needs lots of data samples, so we wouldn't necessarily expect it to do very well. It gets to 52% with just that single sniff. So this algorithm is vastly outperforming. And if you continue to give it more and more data, the deep autoencoder, will learn to classify up to the Loihi algorithms level and beyond. It can get to a higher accuracy level, but it's going to need 6,000 times more data than this single example. So that's, we don't have any theory for that, or not very good theory anymore. We're trying to map this, but this is an example of an interesting novel capability. We don't necessarily know how to generalize this to other problem domains very well. It's a little bit rigid and inflexible, the way this network, this algorithm was developed, but it's certainly a really interesting example that can guide now the theory and this kind of framework of phasers and complex numbered neural network activations as a model for oscillatory spiking processes. Let's see, so another example of work that's been done recently is, this is really shifting gears here, is going to the robotics domain. And we worked with Applied Brain Research. So with their Nengo system, we have they've ported Nengo to interface with Mujoko in combination with Loihi. So you can do this virtual robotic modeling using Nengo and Mujoko, and you know, which of course is much more convenient than doing, you know, real world physical experimentation and development of you know, spike neural net control algorithms. And so as a demonstration of just the capability, they ported their adaptive controller work, which is basically a smart PID controller is how you can think about it. It's if you want to control an arm in this case, where you have the trajectory, all the kinematics and dynamics of the system all modeled, but there's going to be some unpredictable state-dependent perturbations that are introduced into the system. This adaptive control algorithm they have can just learn to cope with those perturbations as a function of, you know, the state space. So this is the first algorithm they implement in this framework, and you can see, you know, this animation that's running now is just a demo of actual Loihi interfaced to a GPU running the whole Mujoko simulation, and then the adaptive control aspect of it running, you know, kind of out on Loihi. And this example, I don't know if, you know, this has been around for a while. This was actually first implemented on a real arm. So going to the virtual domain in this example was actually the out of normal order. But you can see it adapting here when this adapt is on. See the arm has picked up this weight, and it's doesn't have a model of that weight as far as its you know, its control algorithm. So the weight is causing it to deviate from the expected behavior, and the errors based on that, this different weight in the arm is simply getting learned to get the error corrections to the control forces to, this is, by the way, a compliant force activated arm. It's learning how to correct those forces to get it back to the desired trajectory. So it's a supervised learning problem where you have continuous supervision. So that's why, you know, a simple kind of delta rule type of, they call it PES for prescribed error sensitivity, is the learning rule that's running on Loihi to implement that. Yeah, here's another little video of this. This is, in this case, is kind of in race mode. So it's running a version on the CPU as well as then running a version on Loihi. So you can see kind of side by side, you know, how quickly does each architecture run the algorithm, able to adapt and successfully reach the target, and the target keeps moving. So it's just kind of a little visualization of, you know, Loihi is actually running faster in this case because of the faster latency that it offers for this control loop. So it manages to adapt faster, basically, is what that translates to in this example. Okay, so then finally the next, if the slide advances, yeah, another example out on the sensing domain or the edge. So you've probably, many of you know about the DBS gesture data set and gesture recognition with event cameras, and this demo we've had for a while, but this is, if you don't know about it, this is basically our solution using the Slayer tool. And so a Slayer is another backpropagation tool that's available and working for Loihi now. And it's being quite productive in terms of what types of applications and problems it's able to solve. So this is basically applying backpropagation directly to the spiking behavior itself. So not training according to an ANN model, a conventional neural network, and then converting it according to a rate-based activation model. This is more optimizing individual spike times, so it can solve basically arbitrary loss functions. However you may define them, it'll find, theoretically, it'll use gradient descent to find the exact parameters that will satisfy your loss and deal with whatever input spike representation you have in your data set. And so in this case, we're using the DBS gesture data set, and this is a live demo, and this is just captured as a screenshot. This is this demo that works. So this is running, you know, super low power. By the way, this is about 80 times more compact than the True North implementation of the same application. So their solution to the CVS gesture data set that they produced, much more bloated for lower accuracy even, just because of the constraints in the architecture of the True North chip. We can do weight sharing, we can just have much more higher precision weights and all kinds of things, which let us operate with a far more compact model for this. The really exciting recent work is from Emory, and he may have presented on some of this, I don't know, but is actually augmenting the Slayer model for doing this gesture recognition with some output supervised plasticity. So using the learning rules in Loihi so that you can learn new gestures after you've built up a certain, basic capability of understanding gestures. They augment the network with extra neurons, and they use this continuous kind of third factor learning capability that we have in Loihi. And so that then allows it to just kind of classify, learn with a couple examples on new gestures. So that's work that's ongoing, but pretty exciting. And in a similar vein, there's applying this in a robotic sense for tactile sensing. So this is a paper that just came out a few weeks ago at RSS, and this is taking a fusion of tactile sensing and DVS input using Benjamin T's kind of really interesting novel tactile sensors, and then using Slayer to just fuse these two spike streams. So this is an event-based tactile sensor, just like an event-based camera. So you have two spike streams that are corresponding to touch and the visual view of an object. In this case, it's cans, it's various things that, cans and cups and stuff like that you can load with different levels of liquid. So the task here is to detect through vision and tactile sensing what the object is and how heavy it is. And of course, the heaviness is not visible, so you have to be getting that from this tactile sensing. So they have this fused network here, they've trained it with Slayer. What's interesting about how they've trained it is that they can tune the loss function to prefer earlier classifications. So to weight the earlier spikes and try to use time to algorithmically perform faster inference. And so that works very well. It's basically, I don't have time to go through all the results, but you can look at the paper. It's performing as well or better than both a recurrent and a feed-forward conventional neural network for this. And when you run this on a GPU, we're running faster than the GPU on Loihi, doing this continuous time inference. So this is a continuous time problem here, and we're vastly, 45 times lower power. So these are the kind of examples we love, of course, and so I guess I'll finish here with kind of a latest quantitative summary of all the results. So this is like what we're really, more than anything else, we love to see demos and applications and all this stuff. I mean, it's really, but what we're trying to do in our program at Intel is really first take a rigorous approach to understand where is the biggest gains coming in this algorithm, in this domain. Our neuromorphic chips, should we be converting deep networks and running those on neuromorphic hardware? Or should we be doing things like that constraint satisfaction solver, for example? What is really the most exciting class of algorithms that can really get amazing gains? And so this is what we're trying to show here is, as we quantify solution time, meaning latency, or the delay of the task, and the energy, lower being better, of course. Both of these, we're taking the ratio as we evaluate various different workloads, the ratio of the reference architecture to Loihi's value. So the top right on this axis is better for Loihi because we're either much lower energy or we're lower in latency on the y-axis. And then this dashed line is the parity curve. And so everything to the bottom left of this line, Loihi is losing. I mean, it's doing worse. But so an interesting picture is emerging. I mean, I've been showing this chart in more primitive forms for a while, and more and more dots accumulate. And we're at a point where some clear kind of patterns are emerging. I mean, I've circled the obvious one, which is feed-forward networks. These are very questionable. I mean, there's plenty of these that where Loihi's losing, And you know, on the most part, they're the ones that are giving the least gains. I mean, almost, you know, exclusively here. And especially all the blue dots are cases where we've converted networks, or you know, people doing this work with Loihi have converted ANNs to rate-coded feed-forward spike neural nets. And so these, and especially the dots, the size of the markers correspond to kind of a logarithmic scale of the size of the network that's been run on Loihi. So you can see that for this class of network, you go to larger networks and Loihi does even worse. You know, so big, deep feed-forward networks are terrible for these spike-based Loihi architecture. On the other hand, once you go to recurrent networks and you start looking in this top right regime, we get some really big gains. You know, some of them, the constraint satisfaction is this, this yellow, these dots here. And then the lasso problem, these green dots, attractor networks are all in green here. And you can see that these are all pretty compelling. These orange dots are the backprop train networks for spike neural nets. So some patterns emerge here, and the, you know, the bottom line is that you know, we can get order of magnitude gains with this architecture, and if we're careful and we're, you know, we solve some of the composability problems, the software framework issues, which allow us to actually, you know, compose these exotic networks that are emerging, we should be able to get some, you know, really amazing functionality or gains compared to conventional computing, both at the edge and potentially scaled up to you know, very large systems. Okay, so I don't know, yeah, we got all off schedule, but I'll stop there. Hopefully I haven't overrun.
Thank you, Mike. This is an amazing talk with lots of content and quality publication references, some Nature papers coming out and archived papers. Really nice. And the last speaker basically summarized, I guess, everything that we may want to know. You have a lot of questions, but you have not signed up on Slack. So we're going to sign you up and you can respond to those questions.
Will do.
There is a lot of, let me try to answer some from the beginning. When you're, I'm going to go back to the energy. It's something that in the energy delay product, you pointed out. When you're measuring the energy of Loihi, are you using any external measurement device or more accurate measurements, or you're just using the profiling tools in NXSDK?
So the energy measurement methodology has been improving steadily over, you know, since we began. So just last month, I think, or yeah, I think it was last month, we released new capability, which is, so one of the problems with our power measurements historically has been we've had boards that have 32 chips on them, and the workload may be some, you know, couple cores on one chip, and people will take power measurements and you're getting this static power from 32 chips. So there's a signal to noise problem there, right? And so it's, and we didn't establish a clear enough methodology, I would say, for you know, making sure everybody's consistently capturing the same you know, numbers and knowing how to interpret the numbers. So with this latest release, we've tried to make this completely easy and uniform and standardized so that we turn off everything that's not being used as much as possible. And then we report it out very clearly, what is the idle power, what is the active power, and it's still up to you to make sure you set up a nice steady state workload that can be measured, you know, well in that way. But but once you do that, yeah, you get some you know, good consistent numbers from all that.
And there is a question on neuroscience, I guess, related. Can you elaborate on how intrinsic neuromodulation is implemented in Loihi?
Sorry, how neuromodulation is?
Yes, how can you implement neuromodulation?
So we have something called reward spikes, which are basically graded spike values that you can send in, and then this sets a modulatory term, which the learning rules can reference. So that's a bit restrictive. So in the sense that I think each core has support for something like 4 of these reward channels. So you're limited in the total number of these that are available. But that's one way to do it. It's that you send in these reward spikes from, you know, off chip or the embedded processors in Loihi, and based on some external, feedback that may come, and then that can modulate the learning rates or anything about the learning rules. Another approach is to use the embedded processors a little in a more tight way, and that's what Emre has done in his gesture recognition work, to really have a third factor that is scoped to the postsynaptic neuron itself. So you project the errors directly to the neurons and have them have their own kind of modulatory term that's projected.
Terry has a practical question. Are there any commercial applications in the field?
Any commercial applications? Well, yeah, that's the big question, isn't it? So I think I skipped a slide for time, but the outlook, I would say the most compelling is to go and fuse this technology as closely as possible with event-based sensing. I think that is where we're likely to see, the first commercial applications.
I think so too.
Mike, just to raise a question on that, you showed these really nice results on constraint satisfaction, and it seems that they're really on the top right of your last figure. That's kind of independent of those event-based sensing, right?
Yeah, you're right. Well, this is so brand new, honestly, that I don't think we've kind of completely internalized, bringing optimization, really fast, low power optimization into edge devices should be useful for something, clearly. The thing we struggle with constraint satisfaction is, what is the application? Who needs a milliwatt Sudoku solver? We all think Sudoku, or traveling salesman or world map coloring, right? It's like, what can we actually do with that people will actually pay money for? And so I don't have a good answer today. I mean, if anybody does, let us know, please. We'll sell you as many as you need.
Yeah, so
there's a question.
Oh, you mind if I jump in, Andres? So first of all, I love to talk, and to kind of pile on top of that, it's clear that Loihi is getting a lot smarter, and there's great algorithm development going on. One of the really cool things that I think is a huge success story here is that a lot of this is happening in collaboration with the neuromorphic community. People that might be, that maybe you work with here, or maybe there are some people online now, some newcomers to this community that might have gotten some ideas sitting here listening to this talk and are excited to work with you going forward. I know what I'd be working with you on this summer if we were in Telluride. I mean, I think a lot of your approximate nearest neighbor stuff and your LSH, the hashing types of things are getting us to a point where you are getting into a space where a lot of the self-attention networks that are revolutionizing deep learning are working too. We're starting to see, like retrieval from dynamically changing memories being like a really important component of neural networks. And so I think there's a lot of exciting work yet to be done in partnership with the community. So how should people who are engaged in this workshop right now look to contribute to this growing pile of literature?
Absolutely. Yeah, I'm glad you reminded me. This email address is everything. This is all you need to know. If you email them, that email address, we have a engagement process. Us being a big corporation, there is like legal overhead, unfortunately. I wish there wasn't, but yeah, it's just a matter of going through the process. You get access to Loihi, and we're giving out hardware. We have cloud access. Most of this work happens on the cloud, right? So logging in, and of course that's what we're doing. Wherever we are these days, working remotely. So yeah, definitely reach out, let us know, and we can get you access to Loihi and join. We've got over 100 groups now in
do we have time for more questions?
I want to point out, because of the screen sharing, we can't see the email address on Mike's screen. So if we could just put it in chat or in Slack also, we'll make sure we share that around.
So there's another question that actually it's probably a couple of them. I think the answer is in the graph that you show. Some people are asking, how does Loihi compare with accelerators specifically designed for deep neural networks?
So that is some of those little data points in there. We're exactly showing that. So the Movidius, our own product, the neural compute stick. So this is work that ADR did for a small audio classification network, keyword spotting network. Loihi is outperforming by a little bit, factor of 5 or so in energy efficiency, if I recall correctly. So a little better. Now, I think what we see is that for small networks, Loihi can do that well. You get all the parameters on chip onto a scale of what Loihi can handle. It'll be fantastically efficient. Once you start exceeding that, though, you need to start going to multi-chip, a mobile net scale, which is designed for mobile applications. That's where conventional deep networks, like a mobile net, will Loihi will fall over and not outperform. So that's where we need algorithms that are designed to exploit the sparsity of this architecture, not just taking what's off the shelf that have been designed for today's data parallel architectures, whether that's neural compute stick or GPUs or even CPUs. They all have these very wide data paths. So short answer is, if you've got small problems, Loihi, we have examples of Loihi outperforming even edge devices that are optimized for edge processing. But it's a small niche there if you're restricting yourself to existing conventional architectures.
There is other questions, but I think it's probably better if you can answer some of this. There's requests for papers, and presumably